On March 24th, 2026, a researcher named Callum McMahon sat down to test the plugin. Within seconds, his 48 GB MacBook was completely frozen. CPU pegged at 100%. RAM almost exhausted. Even Headstop, the tool you use to diagnose a problem, took 10 seconds to open. He had no idea that his frozen laptop had suddenly accidentally uncovered one of the most sophisticated supply chain attacks in the AI history. Here's exactly what happened and why it matters to every single person building with AI today. Okay, so before we get into the how and why of this attack, I need to make sure we are all on the same page. Because if you are not a developer, the name LiteLLM might mean absolutely nothing to you. And I get that. So let me explain this in simple, plain English. And I promise once you understand what LiteLLM actually does, you are going to understand exactly why it was such a high value target. LiteLLM is what's called an AI gateway or proxy library. In simpler terms, it's a package that lets developers connect to every major AI model like ChatGPT, Claude, Gemini, Mistral, you name it, from a single unified interface. Instead of writing separate code to talk to OpenAI, separate code for Anthropic, separate code for Google's LLM, you write it once with LiteLLM and it handles all the routing for you. Think of it as a universal remote control for all of your AI APIs. And this thing is wildly popular. We are talking about 3.4 million daily downloads on PyPI. That's the Python package registry, like your app store for code. To give you context, that puts LiteLLM in the same tier as some of the most downloaded developer tools in existence. But here's what makes LiteLLM uniquely dangerous from a security perspective because of what it does. Routing traffic to every AI API, it becomes one place where developers store every AI credential they have. Your OpenAI API keys, your Anthropic key, your Google Cloud credentials, your AWS tokens, your database passwords, everything. It's like, imagine if every key to every lock in your house lived on one specific key ring. LiteLLM is like that for thousands of companies, and LiteLLM was that specific key ring. Wiz, the cloud security company, found LiteLLM in 36% of cloud environments they surveyed. That's more than 1 in 3 cloud deployments touching this single package. And it's not just for small startups, we're talking enterprise AI infrastructure at scale. It's also a transitive dependency, meaning 2,337 other Python packages depend on it. So even if you didn't install LiteLLM directly, if you installed any of these packages like DSPy, MLflow, OpenHands, Crew AI, or Arise Phoenix, you were running LiteLLM under the hood, possibly without even knowing it. And that's the core of why supply chain attacks are so terrifying. You think you're installing one thing, you're actually installing a whole ecosystem. I want to take a moment before we get into the mechanics of the attack to really sit with the scale of what happened here. 47,000 installations in 3 hours. Let that land. 3 hours is roughly how long it takes to watch a movie and have dinner. In that window, an estimated 47,000 instances of LiteLLM were running the attacker's malware, silently collecting and transmitting everything they could find. And I want to be crystal clear about everything, what everything means over here. This wasn't a limited credential grab. The malware kind of swept for SSH private keys, AWS, GCP, and Azure credentials, Kubernetes configs, and every secret kind of stored in every namespace. Docker registry credentials, database passwords, MySQL, PostgreSQL, Redis, MongoDB, your CI/CD pipeline configuration, Slack, and Discord tokens. And I really want you to kind of hear this one, okay? Cryptocurrency wallets. Bitcoin, Ethereum, Solana, Monero, even Ledger hardware wallet configurations. That's not just a credential stealer we're talking about. That's a whole lot of digital vacuum cleaner designed to take everything and leave no trace. The malware encrypted all of it with AES 256 before sending it out, which means even if you intercepted the traffic, you couldn't have read it. Only the attackers have the decryption key. Now, here's the thing I want to address specifically for this community, because a lot of you are non-technical professionals who are building with AI tools, using AI in your workflows, maybe even running small AI-powered businesses. You don't need to be writing Python code to be caught up in this. If your company uses any AI integrated software, and I mean almost any SaaS product in the AI space right now, there's a real chance that somewhere in that software's infrastructure, LiteLLM is running. And if their deployment hit the compromised window, that's your company's data potentially in attackers' hands. Of these 2,337 packages that depend on LiteLLM, 88% of them, which is around 2,054 packages, had version specifications that would have automatically pulled in the compromised versions. Not because they were careless, just because they hadn't pinned to an exact version, which honestly most developers don't do by default. And this is the quiet horror of the modern software supply chain. The packages you install, the libraries your tools depend on, the scanning tools that check these libraries, all of it creates this vast interconnected web of trust, and that trust is the attack surface. Gal Nagel from Viz said it best. The open source supply chain is collapsing on itself. Trivy gets compromised, LiteLLM gets compromised, credentials from tens of thousands of environments end up in attackers' hands, and those credentials lead to the next compromise. We are stuck in a loop. And he is right. I'm not going to leave you stuck in that loop. Later, I'll show you exactly how to break it. First, let's understand how this attack actually worked. The attack on LiteLLM didn't start with LiteLLM. That's the first thing you need to understand. The attackers were patient. They planned this over weeks, and they started somewhere completely unexpected. Let's go back to the late February 2026. A threat group called TeamPCP, which we'll talk more about in a moment, identified a vulnerability in a GitHub Actions workflow, specifically in a repository belonging to Aqua Security, which is a well-known cloud security company. The tool they targeted, it's called Trivy, one of the most widely used open source vulnerability scanners in the world. The very tool that development teams use to check their own code for security issues. The vulnerability was in something called a pull request target GitHub Actions workflow. I'm going to explain this without the jargon. GitHub Actions automates software tasks like testing code, deploying updates, running security scans. So a pull request target workflow is meant to run in privileged environment only when code has been reviewed. But if it is misconfigured, it can be triggered by anyone, even someone submitting malicious code from outside the organization. TeamPCP found exactly that misconfiguration in Aqua Security's Trivy repository, and that exploited it to steal CI/CD credentials, the keys that Aqua's automated systems use to publish, sign, and update Trivy. This gives us CVE 2026-33634 with a CVEs score of 9.4. That's near maximum severity. On March 19th, 5 days before the LiteLLM attack, they used those stolen credentials to force push malicious code to 76 out of 77 version tags in the Trivy Action repository. Think about what that means. Every project pulling Trivy to check its security, which is thousands of projects, was now trusting a version of Trivy that was secretly reporting home to the attackers. The security tool had become the attack vector. This is the most sophisticated part of this whole operation. Aqua Security had actually disclosed the initial Trivy incident on March 1st, so they knew something was wrong, but the credential rotation, the process of invalidating old keys and generating new ones, wasn't done atomically. There was a gap, and TeamPCP retained or rederived access during that window. Then they waited patiently for the right moment to use it. So it's now March 24th. LiteLLM CI/CD pipeline runs its regular build process. Part of that process involves pulling Trivy via apt, the package manager, to scan for vulnerabilities. And here's the critical mistake. They pulled Trivy without pinning a specific version. So the build pulled was whatever was latest, which of course was a compromised version. At 10:26 UTC time zone, the compromised Trivy scanner runs inside LiteLLM's GitHub Actions environment. It finds the PyPI publishing token, the credential that allows someone to publish new versions of LiteLLM to the package registry, and it sends it to the attackers. 13 minutes later, at around 10:39 UTC, a new version of LiteLLM appears on PyPI. It's the version 1.82.7, published by the attackers. There is no corresponding GitHub tag, no release notes. The attackers were in. And 13 minutes after that, version 1.82.8, which is an escalated version, which was more dangerous. And here's the 3-hop attack chain, which explained in plain English for you. TeamPCP stole credentials from a GitHub workflow, used them to poison a security scanner. The scanners stole credentials from LiteLLM. LiteLLM's credentials published malware to PyPI. 3 hops. Weeks of preparation, every step exploiting trust. And LiteLLM, with 3.4 million daily downloads, was the crown jewel in all of these things. Coming up, what was actually inside those malicious packages? Because it is worse than what you're imagining right now. Let's talk about the malware itself. The attackers published 2 versions and they escalated dramatically between them. Version 1.82.7 embedded a base64 encoded payload inside a file called proxy server pipe. It only executed when a specific part of LiteLLM was imported, targeted, but it was limited. Version 1.82.8 was the escalation that nobody saw coming. This one placed a 34,628 byte path file called LiteLLM init path directly into Python's site packages directory. Here's why that matters. Python automatically executes path files on every single interpreter startup. No import is required, no special trigger is needed. Every time Python runs, for any reason, the malware runs. And that includes during the pip install process itself. The malware ran before any of your code, before you even knew you'd installed it. Stage 1 was credential harvesting. The malware swept the entire system for anything valuable. This wasn't designed to grab one credential and get out. This was a digital vacuum cleaner optimized to take everything, every type of secret that might be accessible from an AI development environment. 14 plus categories of credentials, all of it encrypted and sent home. Stage 2. This is where getting the data out without being detected. The collected data was encrypted with AES-256 CDC, a strong symmetric encryption standard using a random session key. Then that session key was encrypted using a hard-coded 4096-bit RSA public key. What this means, even if you intercepted the traffic, you couldn't decrypt it. Only TeamPCPs has the private key. All of it bundled into a file like this. So it's a tar file which the TeamPCP had. Then posted to models.litellm.cloud. Note the domain. Subtle brand impersonation. Not LiteLLM's real domain. It was designed to blend into the network logs. Stage 3. It was persistence and lateral movement. The malware installed a systemd backdoor, a persistent backdoor service at this location. This service pulled a second domain called this every 5 minutes, waiting for instructions, additional payloads, whatever TeamPCP wanted to deliver next. They are not done when the credentials are stolen, they are setting up a permanent presence. But the most alarming part was, especially for anyone running enterprise AI infrastructure, was the Kubernetes later movement. If the malware found a Kubernetes service account token on the system, it would read all secrets names across namespaces in the cluster, then deploy privileged pods named node setup, followed by the node name, to every node in the kube system. These pods mount the host file system, which means essentially root access to the underlying infrastructure, every server, every container, every service running on that cluster. This isn't just theft, this is like a full-blown occupation, a persistent privileged presence inside your infrastructure that could be activated later for literally anything. More data exfiltration, ransomware deployment, using your compute for crypto mining, establishing attack vectors against your own customers. And it had a fatal flaw, one accidental bug that would blow the whole operation open. We'll get to that after this pivot. Okay, pause. Before I go into the discovery and the response, which is genuinely a remarkable story in itself, I want to acknowledge something. If you are listening to all of this and feeling scared, feeling like you don't know if you can trust any of the tools you're using right now, I hear that. That is a completely natural response, and I'm not going to be telling you to not feel that way because that is genuinely alarming. But I also want to be honest with you about something. The community response to this incident was remarkable. The speed at which it was found, the way researchers shared information, the transparency from LiteLLM's team once they understood what happened, none of that gets the same headlines as the attack itself. But it matters. The open source security community has immune responses. They are imperfect, sometimes slow, but they exist. And the fact that we know about this attack publicly with CVEs assigned and advisories published is evidence that the system can surface these things. Here's but I don't want you to miss this moment. The response to this attack gave us the clearest possible blueprint for what actually works, and I'm going to give you that blueprint specifically and practically in the next couple of minutes. Let me tell you about Callum McMahon. He's a research scientist at Future Search. On March 24th, he was testing a Cursor MCP plugin, a developer tool integration that pulled LiteLLM as a transitive dependency. He wasn't specifically testing LiteLLM here. He had no reason to be suspicious. He ran pip install on his 48 gig Mac, and within seconds, his machine was completely unresponsive, CPU pegged at 100%, RAM fully exhausted, even Headstop was taking 10 seconds to load. Hard reset, restart, it was the same thing all over again. After that reset, McMahon started investigating. He traced the problem to LiteLLM init path, the path file we talked about earlier. Remember how Python executes path files on every interpreter startup? The malware's payload spawned a new Python subprocess as part of its execution. But when that subprocess started, it triggered the path file again, which spawned another subprocess, which triggered the path file again, which spawned another subprocess, and it went on forever. It was an exponential fork bomb, completely unintentional on the attacker's part, a bug in their own malware. And this is the moment where I have to quote Andrej Karpathy because he nailed it perfectly. He said if the attacker didn't wipe code this attack, it could have been undetected for many days or even weeks. Wipe coded. That phrase, meaning code written quickly, probably with AI assistance that works, but it's sloppy, has become shorthand in the AI community. And the irony that a supply chain targeting the AI ecosystem was itself built with AI sloppily is almost too on the nose. McMahon published his findings on Future Search's blog and opened GitHub issue number this at 11:48 UTC, about an hour after the malicious packages went live. Within an hour, the disclosure had spread to various Reddit forums and Hacker News, where it reached 818 points and 455 comments. The community alarm was working. But here's where it gets even wilder. At 12:44 UTC, less than an hour after the issue was opened, TeamPCP deployed 88 bot comments and 73 compromised GitHub accounts in 1 or 2 seconds to flood the issue. Then used the compromised maintainer account, the LiteLLM's CEO's own GitHub account, to close the issue as not planned. They were actively suppressing the disclosure while the malware was still running on tens of thousands of systems. A new clean tracking issue was opened at 13:48 UTC, and by 15:09 UTC, all malicious versions were pulled from PyPI and all credentials were rotated. From discovery to containment, roughly 3.5 hours. Now, I want to put this in context because the supply chain attack on LiteLLM didn't happen in a vacuum. LiteLLM has accumulated 13 CVEs from 2024 to 2025. 3 of them are rated critical at 9.8 out of 10. There is a server-side template injunction via Jinja in Hugging Face, chat templates, a remote code execution via the deployment function, another RCE via configuration parsing, an SSRF vulnerability, which is a server-side request forgery that can be used to steal API keys with an exploitability score of 88.4%. That's not theoretical, that's being actively targeted by attackers right now as we speak. I want to be fair here. LiteLLM is not uniquely bad. Fast-moving, widely adopted open source projects kind of accumulate CVEs. That's partly a sign of active scrutiny of researchers looking closely. But the pattern of critical and high severity vulnerabilities combined with the supply chain attack does paint a picture of a project where security hygiene struggled to kind of keep pace with adoption velocity. And TechCrunch made a pointed observation. LiteLLM displayed SOC 2 and ISO 27001 compliance badges obtained through a startup called Delve, which has been separately accused of questionable compliance practices. Having compliance badges is not the same as having security. TeamPCP, the group behind this, designated LiteLLM as phase 9 of their ongoing campaign. Phase 9. We've been running this for months across 5 different ecosystems: GitHub Actions, Docker Hub, NPM, OpenVSX, and PyPI. They've compromised Trivy, Checkmark, KICS, 66 plus NPM packages, and multiple VS Code extensions. They have publicly claimed collaboration with $US extortion group for monetization and boasted of stealing terabytes of trade secrets. Security researchers identified 2 notable firsts in this campaign. The first, documented use of Internal Computer Protocol, the ICP, as a command and control channel. ICP is resistant to domain registrar takedowns, which makes it very difficult to cut off. And one of the first documented cases of an AI agent being used operationally in a supply chain attack. Not AI assisted, AI operating. As NVIDIA's AI director Jim Fan kind of warned us, this represents a new class of attacks targeting AI agents. Endor Labs summed it all up. This campaign is almost certainly not over. And they're right. TeamPCP is still operating. The attack surface isn't shrinking. It's expanding, if you will. And this is critical, we have never had a clearer roadmap for what to do about it, which brings me to the part of this video I've been building toward. Exactly what you do practically right now and going forward. Okay, let's talk about what actually you do. I'm going to give this to you in 2 layers. First, if you're a developer or you manage AI infrastructure directly, if you are a non-technical professional who uses AI tools built by others. Both groups have specific actions. Let's first look at the developer layer. Step 1. Check your installed version. Open your terminal, type pip show LiteLLM. If the version reads 1.82.7 or 1.82.8, treat your entire system as compromised. Not probably fine, assume everything is out. The PyPI advisory is unambiguous. Anyone who installed and ran the project should assume any credentials available to the LiteLLM environment may have been exposed. This is the official guidance. Step 2. Remove the persistence artifacts immediately. Delete config sysmon and the sysmon service systemd unit. Check for delete any files in your temp TeamPCP. Look for those. Those are working files from the malware. If you don't remove these, the attacker retains access even after you update LiteLLM. Updating the package is not enough on its own. Step 3. Rotate your every credential, every single one. SSH keys, generate new pairs, update authorized keys everywhere, cloud credentials, AWS, GCP, Azure, rotate all of them, API tokens, every service your environment had access to, database passwords, Kubernetes secrets, and audit your cluster specifically for unauthorized pods named node setup, followed by a node name in the kube system namespace. These are the privileged pods the malware deployed. If you find them, that's your confirmation. Step 4. Check your network logs right now. Look for outbound traffic to 2 domains, models.litellm.cloud with .cloud and not .ai, and checkmarks.zone. If you see either of these in your logs, your data was exfiltrated. That's not suspicion, that's confirmation for you. And step 5, seriously consider rebuilding affected systems from a known clean state. I know that's not a small task, but if the malware deployed Kubernetes pods with host file system access, a clean rebuild is the only way to be certain. Now, layer 2, non-technical professionals. Your action here is to ask questions. Specifically, ask your team, your CTO, your IT department, were any of the AI tools or services we use affected by the LiteLLM supply chain attack? Was LiteLLM in any of our pipelines? Were credentials rotated as part of the incident response? If the answer is I don't know or what's LiteLLM, that conversation is worth having regardless of this incident. Questions to ask your team. What packages does our AI infrastructure depend on? How are we monitoring for supply chain attacks? Do we have a process for rotating credentials if a dependency is compromised? And the most important one, who is responsible for this? Who owns the supply chain security in our organization? If nobody can answer these things clearly, this incident is a perfect catalyst to build those processes. It doesn't have to happen to you directly to be a wake-up call. Let me finish with the structural lessons, because as Endor Labs warned, this campaign is not over. So what do we do at a systemic level? There are 4 changes that would have prevented this specific attack and would reduce the blast radius to the next one. Number 1. Pin every dependency, including CI/CD tools, LiteLLM pulled Trivy without a pinned version. That single decision was the root cause of everything that followed. So pin everything. If a version updates unexpectedly, treat that as an alert, not a convenience. Use your log files. Trust your log files. Number 2, use SHA-based action references in GitHub Actions instead of referencing a version tag, which can be changed by anyone with push access. Reference the full SHA of the actual specific commit you trust. Version tags can be moved, SHAs cannot. This one change would have broken the Trivy attack entirely. Number 3, minimum privileged CI/CD tokens. LiteLLM's PyPI token had publishing rights for the whole package. Scope your tokens to the minimum necessary permissions. Use separate tokens per environment. Rotate them regularly. Audit who can publish. The blast radius of any single compromise shrinks dramatically. Number 4, treat any package that aggregates API credentials as a security boundary. LiteLLM holds every AI key in your organization. That makes it as sensitive as your password manager. Monitor it, audit it, have an incident response plan for it, not as a one-time project, as an ongoing practice. I wanted to end with this. LiteLLM's CEO, Krish Dolakia, posted on Hacker News within hours of discovery. He identified the root cause, apologized, and was transparent. The team engaged Mandiant for forensic analysis. They paused all releases for a supply chain review. This response isn't perfect. The vulnerabilities were real. The trust damage was also real, but the speed, the accountability, and the transparency are a model for what open source incident response should look like. The AI ecosystem is growing faster than any of us can track. The tools are incredible, but with that speed comes real risk. And the best thing any of us can do right now, whether we are developers, business leaders, or people who just use AI tools every day, is to stay informed. Ask the right questions. Don't let "I don't understand the technical details" become "therefore it's not my problem." It is your problem. Now you understand it. And all of those steps that I've mentioned in the previous part as to how to identify if you've been compromised, I've written a completely free PDF, linked it down below. So go download it and then implement them step by step. If this video was useful, please share it, especially with someone in your network who works in AI development or AI security. This is exactly the kind of information that needs to reach the right people fast. I'll link everything in the description: the official advisory, the future search breakdown, and a shareable checklist, as I mentioned, for your team. Subscribe if you haven't already, and I'll see you in the next one.